Hi, my name is Taylor and I'm going to be going over the critical exponents of carbon monoxide. It is best seen as a series of graphs. So that is what I'll be showing you. The first one was finding gamma. As you can see from the equation above, with the isothermal compressibility is proportional to the temperature minus the critical temperature all raised to gamma. So I found gamma to be 0.0701, which is really far off. But the way I found this was I went to the NIST website, which is experimental data found by scientists all over the world. And I plugged all these numbers into Excel and then ended up using a bunch of graphs to show that it works, which we'll see now. So first, KT, the right side of the equation is proportional to KT equals -1 over V times the derivative of volume with respect to pressure at constant temperature. So knowing that I needed that derivative, from the NIST website, I did pressure versus volume, and I graphed those two. But seeing that I only wanted to be getting close to critical temperature and pressure, I zoomed in on this part right here so that I could see it, because it gets more linear, and this part is just kind of not good data. So what I did was I zoomed in. Then, once I was there, I tried to use a linear model, but as you can see with the dotted line over here, it didn't fit very well. So then I found a better model to fit the line, or the curve, as you could say, which was a natural log function. And there's an r-squared value of 0.9973, which is pretty good. There's not that much error. So anyways, that's a graph. So knowing that I need to take the derivative, I took the derivative of this function that it spit out, and I got this equation. So because you drop the log and take the derivative. So that's that graph. So that's all just to get this part right here. So after that, I found KT by multiplying -1 over the volume. Unfortunately, NIST does not give straight up volumes, it gives densities. So I just did density, negative density times that. But anyways, then I took the two sides of the equation and did natural log of those two sides, because I knew that the relationship between the two sides is gamma. So as you can see, I did natural log of the critical temperature minus temperature versus the natural log of the KT, and I got this thing. And I try to see the linear relationship, because there should be a linear relationship when finding gamma. So because I had the curve at the end, I decided that I needed to get sufficiently close to critical pressure. So I took 5 points at the very end of this curve, and I expanded them. And as you can see in this bottom right-hand corner, it becomes much more linear with a 0.9975 r-squared value. So in all, I found gamma, even though it's very far from the actual gamma. The process is right, and it all comes down to like NIST values and if I got sufficiently close to critical pressure. Next we'll be finding beta. So this is the equation that I used to find beta. So the molar volume of the gas minus the constant molar volume is proportional to the critical temperature minus temperature, all to beta. So I got beta equals 0.442, which is pretty reasonable. The real value is pretty much a third. This is the closest I've gotten to any of my data, which is pretty awesome. So finding beta, I pretty much did the same process I did on the other one, minus the derivatives and stuff, because you didn't need to do that for this one. So basically, I graphed the natural log of the critical temperature minus the temperature versus the natural log of the molar volume of the gas minus the constant molar volume, and I got a graph that had a curve on it, kind of like this. So I decided that I needed to zoom in. So I zoomed in and got a pretty linear fit, r-squared being 0.99. So I just needed, again, I zoom in because I need to get close to the critical points, the temperature and the pressure, which critical temperature happens to be for carbon monoxide is 132.86, and the pressure is 34.935 bar. So the next one, the last one, is finding delta. So this is the equation that you need to use to find delta. So it's pressure minus critical pressure is proportional to the molar volume minus the constant molar volume, all raised to delta. So I got delta to be 0.0391, which is really far off again, but we'll deal with it. Then, so I did natural log of the critical pressure minus pressure versus the natural log of the critical volume, the critical constant volume minus volume. And I got this, so I zoomed in to get a linear fit, and I need to get sufficiently close to the critical pressure again. And so I picked 4 points at the end, so you just like the linearity in that. And I got 0.0391 with an R-squared of 0.9701. So obviously this one doesn't have as much certainty, but it's okay. So I just wanted to point out that, again, that the critical temperature is 132.86, the critical pressure is 34.935, and the critical density is 10.85 moles per liter. I got all of my data from National Institute of Standards and Technology, so I'm just giving them credit. That concludes this brief, and I hope you enjoyed it and learned about the critical exponents of carbon monoxide. Thank you.